Good morning, students. In the last class, we discussed about the how the semiconductor junction is formed. So in that, we discussed the main or diffusion current, right? So what is diffusion current and drift current, right? So the motion of the charge carriers. This one is the semiconductor. Here we have P and N. So this one is the junction, which we call as depletion region. So P side we have minus. So in inside we have plus. So this one we are calling the depletion region, right? So what is diffusion current, right? So the motion of charge carriers across the junction. So the motion of the charge carriers across the junction. So that current we call as diffusion current. That means the motion of the charge carriers, that is electrons which are diffused from N junction to P junction, right? So similarly, holes diffuse from P junction to N junction. So these two electrons and holes combinedly together we call as charge carriers, right? So next, drift current, the motion of charge carriers due to electric field. The motion of the charge carriers due to the electric field. So here the electric field is from plus charge to minus, that is positive to negative. So it is denoted by, the electric field is denoted by E, right? So we have two currents, one is diffusion current and another one is drift current, right? So along that we have one is, that is potential barrier. Due to the diffusion of the electrons from N type to P type and due to the diffusion of the holes from P type to N type. So here leaving, during the diffusion of the electrons from the N type, leaving positively charged, and during diffusion of the P types, so holes are diffusers leaving the negative charge. So during the diffusion process, so we obtain the potential that form across the junction. So that potential we call as potential barrier, or we call that one as barrier potential, right? So this is the direction of E here, right? So due to the diffusion of the charges, so there will be a potential barrier. So here this one is positive charge and here we have the negative charge across this junction, right? So this one is positive and here we have negative, right? So this potential we call as barrier potential and it is denoted by VP or VO, right? So what is barrier potential or potential barrier? We call this one as barrier potential. barrier potential, right? So there is a development of the potential due to the diffusion of the charges, right? So the potential is developed due to the diffusion of the charges, that is nothing but the electrons and holes we combinedly called as charge carriers. So due to this charge carriers or diffused across this junction, there is a development of the potential. So that potential we call as barrier potential, right? So what is barrier potential? The potential developed across the junction, the potential which is developed across the junction, right? So this one we call as the junction. So here one potential is developed due to the diffusion of the charge carriers, due to the diffusion of the charge carriers, right? So across the junction due to the diffusion of charge carriers, right? So this one we call as barrier potential, right? So in the last class we discussed that is the formation of the junction, right? So due to this junction, that is due to the diffusion of the charge carriers, we are obtaining the potential. So that potential we call as barrier potential. So this barrier potential is denoted by Vp, or we can denote that one as Vo, that is V naught, right? So this is about the formation of the PN junction, right? So this junction we call as PN junction, right? So from that we discuss that is diffusion current, drift current. So along with that barrier potential, right? So next, semiconductor devices, right? So examples of the semiconductor devices we discussed, one is diode and another one is the transistor, right? So transistor is removed from your syllabus, so only we have to discuss that one is the diode. So that one we call as semiconductor diode. Semiconductor diode, or simply we call this one as the diode. So semiconductor diode is a simple type of the PN junction. PN junction semiconductor, so connected with the two metallic strips on either side of the semiconductor, that is either side of the PN junction. So two metallic conductors are connected, so this device we call as semiconductor diode, right? So calling here the terminal A and here terminal B, right? So these two are metallic strips or metallic conductors, so which is connected on both sides of the PN junction, right? So what are semiconductor diode? So semiconductor diode is a simple type of PN junction semiconductor, right? So it is a simple type PN junction with metallic contacts or metallic strips, metallic contacts to apply the potential across the junction, right? So why we are going to place these metallic strips means by this we are going to apply some external voltage for this PN junction semiconductor, right? So that device we call as semiconductor diode. So semiconductor diode is a device, right? So this diode is a device. It is a simple type of the PN junction semiconductor connected with the two metallic strips on either side for the apply of the external potential. That means we can connect this PN junction to the external source, right? So that purpose we are added the metallic contact, right? So what are diodes? So diodes are the devices, right? So that is formed by the simple PN junction, that is simple PN junction semiconductor connected with the metallic strips to apply the external voltage, right? So this is the semiconductor, right? So the symbolic representation of the diode or semiconductor diode is like this. So this one is the symbolic representation. So in the circuit, if you are placing this one, so it indicates what? The diode. So here this arrow mark represents P type and this straight line represents N type, right? So this arrow mark shows the direction of, so arrow mark shows the direction of conventional current, that is flow of the electron. So that one we call as the conventional current. So arrow mark is towards right side means the direction of the flow of current is towards right side, right? So next, so it is a two terminal, it is a two terminal device because it has two ends. So here one end and here another end. So that's why the semiconductor diode we call as two terminal device, right? So next, what happens when we apply the external potential to the semiconductor diode? So in that we have two types. So PN junction is connected to forward bias. So here bias is nothing but applying the external voltage. So external voltage we call in that one as bias. So what is nothing but forward bias, right? So bias is nothing but the voltage we are going to apply, right? So bias is nothing but the voltage. So what is the meaning of the forward bias? So this PN junction diode is connected to the voltage in such a way that right. So forward bias means this voltage. So voltage, that is here we have battery. So one is positive terminal and another one is negative terminal. So positive is always its length is more compared to that of the negative, right? So this one we call as the external voltage. So now we are going to connect this PN junction diode to the external voltage in such a way that the P type of the semiconductor is connected to the positive terminal of the battery, right? So P type is connected to the positive terminal of the battery and the N type is connected to the negative terminal of the battery. So this type of the connection of PN junction to the voltage we call as forward bias. That means P type is connected to the positive terminal of the battery and N type is connected to the negative terminal of the battery. Now, if you observe here, so this one is the voltage. So this voltage we call as applied voltage, right? So this one is the external source. We are going to apply the voltage to this semiconductor, right? So now if you observe here, already we have one potential. So that potential we call as VB or V0. That one is the barrier potential, right? So now if you look here, comparing these two potentials, that means here we have one potential and also here we have one potential. So this potential is induced due to the diffusion of the charge carriers in the semiconductor, right? So now if you observe here, so this one is the VB, right? So now if you observe here, the applied voltage is like this, that is V. So from this, what we observe here, the external applied voltage is opposite to that of the barrier voltage, that is barrier potential, right? So here in the left side we have positive terminal, in the left side we have negative terminal. That means the barrier potential is opposite to that of the applied potential. That means here the flow of charges is positive, so here the flow of charges is negative. That means here the barrier potential is opposite to that of the applied voltage. So what happens when the barrier potential is opposite to that of the applied voltage means, so this depletion layer is get reducing, right? So initially it is at a distance somewhere here, that one is the depletion layer. As we apply the external voltage which is opposite to this barrier potential, so this depletion layer is goes on decreasing, right, like this. So that means here and here gets vanished. So now if you observe here, the depletion layer is decreased, right? So as the depletion layer is decreasing, so the number of charge carriers which are diffused from N type to P type and from P type to N type is increases. So as this diffusion is increases, that means it can easily pass through this barrier. That means easily pass through this potential because the depletion layer is very small, right? So for that, this reason, as the depletion layer is decreases, automatically the flow of current is increases. Flow of current is increases, right? So when we connected, the applied voltage is opposite to that of the barrier potential. So as these two are opposite, then this barrier potential, due to this barrier potential, the depletion layer goes on decreasing, right? So for low voltages, that is this V is less than barrier potential, then current is very less. That is the current which is flowing in the external circuit is very less, right? So as the applied voltage which is greater than the barrier potential, then current which is flowing in this external circuit is more. So from this we can say that in forward bias, so in forward bias what happens, so the offer of the resistance by the PN junction is very less. So the resistance offered is very low because we have more number of the current which is flowing in the external circuit. So for that reason the resistance offered by the PN junction is very low, right? So here the magnitude of the current which is flowing in the external circuit is in milliamperes, right? So the magnitude of the current which is flowing in the external circuit is of the order in milliamperes, and the total current which is flowing in the circuit is equals to the sum of the charge carriers, that is due to the holes and due to the conventional current, that is IE, right? So this is what happens when we did, that is PN junction is connected with the forward bias, right? So in forward bias what happens? The potential barrier is opposite to that of the applied voltage, as due to the potential current is opposite to that of the applied voltage, the depletion layer is goes on decreasing and more number of the charge carriers are diffused from P to N and from N to P. Right? So as this barrier is very small, easily the number of electrons and number of holes are easily diffused, right? So for that reason, the potential is goes on decreasing and the current is goes on increasing, right? So as current increases, this PN junction we call as low resistance PN junction. So this is when it happens when it is connected to the forward bias, right? So now if we take over the points. So the first point is, so when we say that one is forward bias, when PN junction is connected in such a way that P type is connected to positive terminal of the battery and N type is connected to negative terminal of the battery. Right? So this is the definition of the forward bias. Then diode is forward biased. So next point is, in forward bias, the external voltage or applied voltage, external voltage or applied voltage is opposite to the potential barrier, right? Opposite to the potential barrier, hence width of the depletion layer, hence width of the depletion layer decreases and hence height of the potential barrier decreases. So this one is the second point. So this one is the definition of the forward bias. So next, what happened when the PN junction is connected with the forward bias? That means the depletion layer width is decreasing and the height of the potential barrier also decreases. So here we have, this one is the potential barrier voltage. So this is VB or V0. That one is the potential barrier height. So as this depletion layer decreases, then the potential barrier height also decreases. By how much? That is by how much we are applying the voltage, right? So this one we take on as 1, right? So the next point is when applied voltage is when applied voltage is small to that of barrier potential, that means V is less than VB. V is less than VB. So there is slightly decrease in depletion layer, slightly decreasing the depletion layer, and less current is flowing in external circuit, right? So the next point is when applied voltage is more than barrier potential, that means V is greater than VB, then depletion layer decreases, and more current is flowing in external circuit, right? So as the more current is flowing, nothing but so PN junction diode in forward bias offers low resistance, right? And the last point here is the total current is due to sum of conventional current and current due to holes, right? So current is of the order usually in milliamperes, that is MA, that is usually in milliamperes. So as we increasing the external voltage here, the barrier potential is goes on decreasing. So because this one is second, so here is third, right? So this is V minus V, VB minus V. So this is the height of the barrier potential. As we applied voltage is more than that of the barrier potential, so this height goes on decreasing. So as the height decreases, the flow of charge carriers is more. So this is what happens in forward bias, right? So next is when PN junction is connected to reverse bias. connected to reverse bias. So here also bias is nothing but the voltage. So reverse bias is nothing but opposite to that of the forward bias. That means here we have P N. Right. So in reverse bias, what happened? So in forward bias, we connected the external battery, that is positive terminal is connected to P type and negative connected to N type. So here we are reversed that one, right? So here negative connected to the P type and positive is connected to the N type. So here it is minus and here it is plus. So this one is the external applied voltage, that is V. Right. So here in the diffusion region we have the potential, that is barrier potential. It is always from minus to plus. So here it is V. Right. Now if we observe here, the applied voltage and the barrier voltage both are in the same direction. Right. Here minus plus. So here also applied voltage is minus plus, right? So as the potential we applied and the barrier potential both are in the same direction. So in forward bias, what happens? If these two are in opposite direction, the depletion layer is goes on decreasing. But here what happens? Both are in the same direction, so the depletion layer is goes on increasing. Right? So initially we have the depletion layer is here. So when we apply the external voltage, the depletion layer is increases, right? So as the depletion layer increases, the flow, that is diffusion of the charge carriers, that is electrons and holes, is very difficult to cross this barrier because of this potential. Right? So understanding this one, as this barrier is goes on increasing, so the diffusion of the holes to N type and electrons to P type is not possible due to because of this barrier potential. That means the region between P type and N type semiconductor is increased because of the applied voltage. So there is no flow of charges, that is charge carriers from P to N type and from N to P type. That means the flow of current in the external circuit is almost zero. That means there is no flow of the current in the external circuit, right? So but due to some of the minority charge carriers, so only few electrons are able to diffuse from P type to N type and from N type to P type. That is only few electrons. That means here we have minus and here we have some plus, right? So that means the current flowing in the reverse biased circuit is very less, right? So it is of the order micro amperes. That means its order is 10 to the power of minus 6 amperes, right? Only few number of the charge carriers are get diffused. So for that reason, only few number of the charge carriers are get diffusing. So the current which is flowing in the external circuit is very less, and it is of the order of micro amperes. So that is because of the applied voltage is in the same direction of the potential barriers. So as we increases the applied potential, so this depletion layer is also goes on increasing in the same way. So here, so this one is the barrier potential, right? That is VB. As this voltage is increasing, the height of the barrier potential is also goes on increasing, right? So in the reverse bias, what happens? This depletion, that is height of the barrier potential, is goes on decreasing as we increases the voltage. But here what happens? As we increases the voltage, the height of the barrier potential is again goes on increasing. So as this depletion layer is goes on increasing, so the number of diffusion by p type and n type is very less, so only few amount of the charge carriers are get diffused, hence we are getting the low current. So as we are getting the less current, hence we say the reverse biased PN junction is highly resistance. So it offers high resistance. So in forward bias, what happens? Only it allows in forward bias maximum number of the charge carriers are get diffused, hence it is less resistance, that is in forward bias. But in reverse bias, only few charge carriers are get diffused, right? So for that purpose, we say the when PN junction is connected to the reverse bias, so it is highly resistance, right? Next, here we have the applied voltage V and the barrier potential VB. When this applied voltage V is approximately equals to the barrier potential, so until we are applying the potential, that is from low value to high value, right? So as we discussed in the previous, in forward bias, that is V is less than VB, then V is equals to VB and V is greater than VB, right? So here less number of current is flowing, so here equal number of the charge carriers are diffusing, so here we are getting normal current I, so here we are getting more current, right? So that is in forward bias. So in reverse bias, as this potential is less, so if we apply this potential is less, then there will be no chances to cross this potential barrier, right? So hence we are getting the current is 0. When this potential is nearly equal to the barrier potential, right? So for that current is very less. As this potential is increases, right? As this potential is increases, then current is slightly, that is current is sharply increased, right? So that current is the negative direction, that current is in opposite direction, so that current is sharply increased, so that voltage we call as breakdown voltage. So that voltage we call as breakdown voltage. So this is about the forward bias and reverse bias. That means what happens when an external voltage is applied to the PN junction diode, right? So in the next class we will discuss the characteristics, that is current to the voltage characteristics. So from the graph we can easily understand, so what is breakdown voltage, how the current is sharply increases, right? So in the next class we are discussing about the characteristics. So this one is very important, that is IV characteristics. So they may ask for 3 marks. So in the lab also we have the experiment on this IV graph, right? That is forward bias and reverse bias. So in the next class we will discuss. Thank you.